Okay, good morning, everyone. Welcome to our last class. And here is the first slide of our last class. It is intimidating. This is, of course, the Schrodinger equation. I have it in three different versions. This is its most general form. Here, this is a slightly simpler form, which at least shows what the Schrodinger equation is at its fundamental level. It's nothing more than a statement of the conservation of energy. These very strange terms here. Just the first term represents the kinetic energy of, this is about the electron. We're trying to understand the electron, particularly in the atom. That's where Schrodinger started. This equation is much more general than that, but our focus has been on the atom and trying to understand the periodic table, and that's where our focus will be. So the energies we're talking about here are for a stable atom in the ground state. Hydrogen would be the simplest with just one electron, but even for more complex atoms, like for example, oxygen with 8 electrons, this equation would also govern if we knew the energies of the various areas of we know dominated by the nucleus, the energies created by the nucleus. This equation will give us, well, what I'll try to explain, the so-called wave function. So this is slightly a simpler version than this guy here, and then the simplest of all, which we'll focus on, try to talk about, is the so-called one-dimensional steady state. Okay, so what do we mean by all of this? All right. Before we do that, just to make the point that this equation, although looks so foreign to us, like where would you come up with something like this? Where does this come from? Well, it's not so strange. This, in fact, is a wave equation. This is an equation that you would see similar for sound, or for water waves, or for traditional electromagnetic light waves. Okay, uh, equations like this were very familiar to physicists here in the 1920s. What Schrodinger was able to do without a derivation, there's really no derivation for this formula. He played around with the form of the equation he was looking for. He needed a wave kind of equation. This is what wave equations look like. And, well, was able to put something together that works. There really is no derivation, strangely enough, of the Schrodinger equation. It was a brilliant guess, but knowing the forms that he was looking for. But just to show you that it's not so strange, this term here is claimed to be the kinetic energy term of the equation. Here's the potential energy term, and here's finally the total energy term here. V is the general letter that's used in physics for potential energy. And here is what we're looking for. Here's the solution to the Schrodinger equation. This is the wave function. And this is what we'll be talking about. This is when you read about quantum mechanics in a popular presentation or a popular lecture, they're always talking about the wave function. This is the wave function, this thing here, this thing here. We're trying to find a wave function, whatever that is, that makes this equation true, that makes this statement of the conservation of energy true. And I just wanted to show, just take the kinetic energy term and see that it maybe is not so crazy what this is. Here's the traditional kinetic energy. It's 1/2 mv squared. Okay, this is from classical Newtonian physics. Allow me to multiply top and bottom by m. So I have an m squared up on top and an m down the bottom. Notice that this here is the momentum squared. Okay, momentum is mv, so this is the momentum squared. So I can write the kinetic energy as the momentum squared over 2m, which you will see very often in both in quantum theory and in special relativity. It's a very useful connection between kinetic energy and momentum. And finally, if we use the de Broglie wave formula, we know that the momentum is h over lambda. And so the momentum squared would be h over lambda squared. And so now look at this term here compared to this funny looking term here. Here's our h squared over 2m, okay? Same term. And what this is a complicated thing, okay? This del sign here squared, it's taking the del, whatever that is, of the wave equation. This is talking about how the wave equation changes in space. That's what this term is talking about. And here we have in that simplest version, we have lambda squared, which of course is the wavelength. So there is some kind of notion here that these terms don't come from, literally nowhere. All right. Before we take a look in more detail at the Schrodinger equation, let's just mention the Dirac equation, the Dirac electron equation. This is a generalization of the Schrodinger equation. You'll notice that same term here of the wave function over time in the most general form, and the other parts of it are different. They look quite different. This is a generalization of the Schrodinger equation. This does more. This tells us more about the electron and all of its different manifestations, not only in the atom, but in the excited atom and in other places where, electrons, where electrons can lurk. This is the ultimate equation still today to explain the behavior of electrons. This equation we're not going to try to talk about. But where it comes from is what Dirac was doing. He was trying to generalize the Schrodinger equation to take care of the issues of special relativity. When the speed of the electron gets up so high, close to the speed of light, that even the Schrodinger equation and its wave function solutions really break down, just the way the Newtonian equations break down for regular particles as the speeds get higher and higher towards the speed of light. This is what Dirac was able to do. He was able to do even more because this equation predicts one of the elements that the Schrodinger equation couldn't, that fourth quantum number, okay, the spin number, the famous spin of the electron. The Dirac equation handles that, predicts it, and predicts its proper values. But even more importantly than that, the Dirac equation does something which the Schrodinger equation does not do. The Dirac equation predicts for electrons, some of them in some circumstances having negative energies. That's impossible in a sense, in a classical sense, and also up until this point in terms of quantum theory, impossible. There's no such thing as a negative energy. But yet there it was in the formula. And in fact, it was an important that term showing in certain circumstances negative energies was an important element of the equation. It again led to the proper, special cases of the Schrodinger equation, which then didn't show. Make a long story short, these negative energies, these electron solutions in which the electrons seem to have a negative energy, had to be taken seriously. It had to mean something physically. And Dirac thought about this for a long time, for a few years, having different theories about what was going on. Finally, hit upon the famous idea of antimatter. What these electrons were with negative energy were in fact electrons for all intents and purposes, but instead of having a negative charge, they had a positive charge. And that's what gave them, in the formula, in the equations, it gave them their negative energy. Again, we can't go through the details of this. The point is, it was the Dirac equation which predicted antimatter. In the first instance of antimatter, the anti-electron, which we call the positron. This was discovered very soon after Dirac finally gave a clear prediction of what this interpretation should be. So I wanted to mention this just to give the closure of all of the basically new theoretical ideas of the original quantum mechanics. This pretty much with the Dirac electron equation pretty much closes the story of quantum mechanics through the 1920s, and the rest really follows from that fundamental basis. And I just wanted to show this picture. Here are the three great theorists. This is Dirac and Heisenberg and Schrodinger. They're on their way to collect their Nobel Prizes. They were not given all in the same year. Two people were given Nobel Prizes at the same year, and one was by himself, but they all collected them at the same year for some reason, which I forget. And they're accompanied not by their wives, or by one wife. Here is Schrodinger's wife, but this is Dirac and Heisenberg's mother. So it just shows you these guys just, they have no time for any kind of social life. They're totally dedicated, to their physics. They're the ultimate nerds. They eventually will marry very soon, actually, after this picture was taken. But to go to the ceremony to collect their Nobel Prize, yeah, Dirac and Heisenberg took their mothers as dates. I think that's very cute. Okay. Well, take a deep breath, guys. I want to try to explain what the Schrodinger equation is, and more importantly, what is the solution to a Schrodinger equation? It's the wave function. That's what I want to try to get some idea of. You will not get much of an idea of the wave function when you read most popular books on quantum theory. And when you listen to the YouTube lectures, even the ones that I've recommended, but all you'll get is the speaker will wave their hand in the air and say, well, it's just a wave. And that's about as far as it goes. Quantum mechanics fundamentally is an interpretation and understanding of the equations of quantum mechanics. This is unique in the theories of physics, that all that you really have are the equations. Certainly there are equations in every single theory of physics. There's equations in Newtonian mechanics and there's equations in relativity, but there's a physical basis that you can talk about to explain what these equations are talking about, what they're describing, what's really going on that the equations describe in some way, or reflect, explain even in some way. This is not true for quantum mechanics. The equation of quantum mechanics, and we're going to focus on its fundamental one, the Schrodinger equation, doesn't tell you anything directly about what's going on. As a matter of fact, still to this day, there's a controversy as to just what the Schrodinger equation and its solution is exactly saying. This is unique in physics. There's no other theory that has different interpretations. There's no different interpretation of Newtonian mechanics or special relativity or thermodynamics. There's one interpretation because it describes the real world in a certain way. That description makes sense to us. It's confirmed by experiment. And so we have a mental picture, a model of what's going on that these equations reflect. This is not the case for quantum mechanics. And the culprit that we will point to is the Schrodinger equation. The controversy about just what the solution to the Schrodinger equation is. That's what I'd like to get after, because if we're going to have some understanding of quantum theory, quantum mechanics, and what makes it so different, I want to make an attempt to talk about the solution to the Schrodinger equation and what's so strange about it, what's so unique about it in terms of the rest of physics. So here's my attempt. A different type of equation. Here's an equation which we're very familiar with, an algebraic equation, 5x is equal to 10. This is a statement about the number x, right? It says that 5 times some number is equal to 10. And the solution is obvious. 5 times 2 is equal to 10. The point is the equation says something about x. And the solution to the equation is the answer to that question. 5 times some number is equal to 10. What is that number? Okay, we're familiar with this. Equations which have solutions as numbers. The different type of equation, in which Schrodinger equation, dirac equation, is an example of, is called a differential equation. Virtually all of the equations of physics are in one form or another differential equations. And if we look at this equation here, the first thing I want to tell you is that the unknown in this equation is not a number. The unknown in this equation is right here. It's read x of t. This is not a multiplication. This is not x times t. This is a piece of notation. It says that the number x depends upon the number t. That is, I can compute for you a whole series of x's if you just give me a whole series of t's. If you give me a t, this function will tell me how to compute x. X depends upon t. Okay, that's what this is. What I'm looking for is a rule which tells me how to compute x given the number t. X and t are numbers, okay? But there's a relationship between x and t, and that's what this notation tells me. It tells me that x is determined by t. And finally, the full equation says, since x is determined by t, when t is changing, certainly x will be changing because t determines x. So what this tells me is that x is changing 10 times faster than t is changing. That's what this says in words. Just as this says 5 times some number is 10, this tells me that the number x depends upon the number t, and in that dependence, the way x changes is 10 times faster than the way t changes. So it says a lot. The richness of the language of mathematics. What this says is that the number x, which is determined by the number t, is increasing. That's here 10 is positive. If I had 10 being a negative number, if this was a negative 10, it would be decreasing. But here I chose a simple positive 10. So that x is determined by the number t. That's this notation here of x of t. That x is determined by the number t, and x is changing 10 times faster than t. And the solution is not a number. The solution is, in fact, a function of t. It tells me how to compute x given t. And the answer is simple. When you think about it, after all is said and done, x is simply 10 times t. So when t is 1, 2, 3, 4, x is 10, 20, 30, 40. And sure enough, as t changes by 1, x will change by tens. So x is changing 10 times faster than t. This is the solution to this differential equation. But notice it's not a number, it's a rule of how to compute x from t. X depends upon t. And even to emphasize even more that x is not a simple number, x in fact has a graph. As t is 1, 2, 3, x takes on the values 10, 20, 30. Surely, as t changes, x is changing 10 times faster, which is what the equation told us to find. So this is a differential equation. The Schrodinger equation is a differential equation. So let's take a look at this version of the Schrodinger's equation. This is that intermediate value of the intermediate instance of the Schrodinger equation. This is what we're looking for. This is the answer. This is the solution to the Schrodinger equation. It's called psi. And this is the wave function. And notice that psi depends upon r. R is simply a position in space. You specify r by telling me the point in space that r represents. I need the x and the y and the z coordinate of r. And you give me those three numbers. Psi of r will give me a value. It'll give me a number. It'll show me how to compute what the value of the wave function is at that particular place. That's all that is. Okay? That's what psi is. Psi is a rule, which you give me a place and I'll compute for you a number. And now what the Schrodinger equation says is that rule, that function has this relationship. Here's the total energy of the system, the atom that we're talking about. Here's the potential energy. Notice the potential energy also depends upon R. The potential energy is itself a function. You give me that same place, I'll tell you what the potential energy is at that place. Okay? This is something that has to be known in order to solve for psi. We can't have more than one unknown in the equation. So we have to know the potential energy, how the potential energy changes in space as we move through the atom, dominated by the nucleus. This should be a known function so I can find the unknown function, the wave function psi. So here's the potential energy term. And this complicated thing, the kinetic energy term, this tells me how the wave function changes in space. As I move from place to place, this tells me how it changes. The analogy of x changing 10 times faster than t. Clearly, this is a much more complicated potential relationship of how the wave function can change in space. Okay. What does a wave function look like? What does a solution to this equation actually look like? Well, an example would be like this. This is what the solution to the Schrodinger equation could look like. Here I've simplified R to not have a point in space, but just a point in the plane. Just a point that just has an x coordinate and a y coordinate. So every single point here has an R. For example, this point here has an x value of 6 and a y value of 4. So this point here is called 6, 4. This is just our graph. You give me 6, 4 in R, and psi will compute a number. That's all. There's a number that's associated with this point, 6, 4. And it's a green kind of number, okay? So I look over to the green, and it has a value of 226. That's what psi is doing. You give me a place, and I'll give you, and give me two numbers so I can specify the two coordinates, and I'll compute, psi will compute for you a number. Because of the form of this differential equation, the answer, its solution, is in the form of a wave. Because you can see that the red areas are the high areas, the green and the yellow and the intermediate, and the blue areas are the low areas. So this is a wave. This represents a wave. I go from high down to low, back up to high, drop down to low, go up to high again, and then we'll way down to low. And no matter how I move through this thing, I'm moving in a wave kind of form. Now, this is not such a strange thing. We actually, this is a quite familiar thing to us. This is nothing more than a topographical map. Okay? This is if we take a mountainous region and record the height of the region at any place, I would get this map. This just tells me the height that I would be at if I was standing at this place on the grid, a topographical map. Okay, so that's all. That's an example of what psi could be, and certainly it does describe a wave type of situation because the altitudes, the heights of the mountains are changing all the time. All right, I want to simplify this one more time so we can get into our atom. But before we do, let's take one look at the most general Schrodinger equation. What's different about this thing here? If you look carefully, psi, the wave function, not only depends upon where you are, but it also depends upon the time. Yes, I have to give you where I am in the atom and the time. As the time changes, the wave function will change, even though I'm staying at the same place. Keep R constant. As time changes, psi will give me different values for different times. That's a much more general situation. What would be the physical counterpart here? This would be this mountainous area during an earthquake, where some parts of the land would be going up and some part would be collapsing down. And even if I looked at one point, Okay, if I stood at one place, I would be knocked up and down by the power of the earthquake. The actual whole topography would be changing with time. Clearly a very, very complex situation. That's the most general solution to the Schrodinger equation. That would be the most general wave function. We're not going to try to talk about that guy. Okay, we're going to try to take a look at the time when the wave function is static, that has a steady state solution, that it doesn't change with time. And when would those be? Those would be the energy states of a quiet atom in its ground state. It's not being excited by any energy input. So the electrons are in their places. Let's say you took the oxygen atom with its 8 electrons. It would be in 8 different energy states, possibly, and they would be static. The energy states would not change. And therefore, the wave function for each one of those 8 electrons would not change. They all would be waves, that's for sure. They all would have different heights as you went out to different distances from the nucleus. They would all be a wave phenomenon. You give me a distance out from the nucleus, and I'll give you the value of the wave function of the 5th electron, which will be different from the wave function of the 6th electron. But at least the wave function of the 5th electron isn't changing because its energy is not changing. A simpler situation. That's the one I would like to try to get some handle on. All right. Here's my attempt. Here's our solution of the wave equation for R. And let's focus just upon one value of y. Let's take just y equal to 1. And just let x change. It's here from 0 to 9. Remember what these numbers are. These represent distances out from the nucleus, okay, for an electron. So I'm holding one coordinate fixed and just moving along one direction, out. And it doesn't really much matter what direction I'm moving in. Notice that this itself, just along this line, is a wave. We go from high, down to lower, back up to high, down to lower, high, and then all the way down to low. This is yet a wave, but the wave only depends now upon x. You give me an x value and I'll give you a height. All right. The simplest wave I can think of would be the sine wave. This is not a sine wave. This is much more complicated, as we can see, but this would be the simplest example of a one-dimensional wave equation. This is not the wave equation that we're going to find for our hydrogen atom or any atom. It's just the simplest one we could possibly imagine mathematically. So allow me to just mention what the characteristics of this simplest solution possible of the Schrodinger equation could be. It's a wave. Here's our psi function. This is actually the solution to the Schrodinger equation. And notice, of course, it is a wave. As you give me different x's, I'll give you different heights. Psi is a way of calculating the height at different distances, moving further and further away from the nucleus. Okay. This is the wave equation. This is the solution to the Schrodinger equation. What does it mean? Nobody really knew exactly what this meant. What Schrodinger thought it meant at first was it gave kind of like the density of the electric charge. The electron, after all, is a negative charge, and this would tell you that the electric charge was very dense. It was a lot of electric charge here close to the nucleus. It would go down to 0. It would become possibly a negative electric charge. Then it would all of a sudden start to rise again. This would give a measure of the electron kind of smeared out in space. This was Schrodinger's original idea. This is what he tried to make work. Couldn't make work. This is in fact not what the wave equation is. But before we take a look at what the traditional interpretation of what it is, this wave equation has this wave function has an equation, and not surprisingly, it's the sine curve, the sine function. And these three numbers, A and W and K, give characteristics of the wave. A is the amplitude of the wave. It's the highest point. It's the furthest that the wave reaches from the equilibrium point. W will give the frequency of the wave or the wavelength of the wave. K will tell me where the wave starts. The value of K will tell me, does the wave start at the origin here, or maybe the wave starts here, or maybe the wave starts here at the origin. So these three numbers give the characteristic of the wave function, the solution to the Schrodinger equation. And this is the Schrodinger equation, the simplified version of it, which would give that as the answer. Okay? This equation has this solution in its simplest form. Here's the total energy part of the equation. Here is the potential energy part. Notice the potential energy also depends upon X. As you move further and further away from the nucleus, tell me how the potential energy is changing. What's the potential energy at 1 unit away? What's the potential energy at 2 units away? This is what this will tell me. And this tells me how the wave function is changing as the distance from the nucleus is changing. This is a possible solution to this equation, the simplest one that we can think of. But what does it mean? What does the solution to the wave, to the Schrodinger equation mean? It's a wave. Why is it a wave? Because Schrodinger cooked it up that way. He cooked up the differential equation, which he knew would give a wave equation. Okay? Just as we know that y equals mx plus b is a straight line equation, he knew that the form of the differential equation he was using would give a sine cosine combination type solution. He knew he wanted a wave equation. He thought he was going to get the distribution of the charge in space from his solution. Didn't turn out that way. The brilliant interpretation comes from Max Born. It's ironic because Max Born was the mentor to Heisenberg and Pauli, who the ones who developed the matrix equation. He turns around and takes a look at Schrodinger's solution and says, just as he had to tell Heisenberg what his mathematics was, he had to tell Heisenberg, actually what you're dealing with here are matrices. Born also had to turn around and tell Schrodinger what he was dealing with. He says, no, you're not dealing with the density of the actual electric charge of the electron. What you're doing is if you take the wave equation, the blue line, and multiply all of its values by itself, square every single value, you'll get another wave. Okay, you'll get this red wave. For example, when the blue wave is 0, 0 times 0 is 0. So the red wave is also 0. When the blue wave is 1, 1 times 1 is 1. So the red wave will be 1. But when the blue wave is -1, -1 times -1 is also 1. When the blue wave is a half times a half is a quarter. When the blue wave is minus a half times minus a half is also a quarter. So by squaring the wave equation, you get an equation, a wave, which is at least always positive. Okay? And it'll simply be the square of that simple sine curve. But this red wave has no negative values. This red wave looks much more like a probability distribution. And that was Born's great insight. That with some manipulation to make it, in order to make this wave changing value be a probability, the whole thing has to add up to 1 because it's got to be someplace. So the sum of all the probabilities are 1. What this would mean here is that this place here, at this distance here from the nucleus, there's no probability of finding the electron. You'll never find it here. You have a high probability, the highest probability of finding it here. The reason why the wave goes out in both directions is because, well, you can move in this direction from the nucleus, you can move from this direction from the nucleus. It's basically the same probability distribution. That's the reason why we can have negative x's. Nothing strange about that. And so let me read this very carefully because this is often misunderstood. Max Born gave the interpretation of not the wave equation, but the square of the wave equation. And listen to the words very carefully. It says, Upon measuring the position of the electron, after you've measured it, take any time you want, take some spot, take some time, and go ahead and measure a particular electron that you're interested in any atom that you're interested in. Measure it. What you will find is that the probability of finding the electron at that place X is determined by the chi-squared value. The chi-squared value isn't exactly the probability of finding the electron at that distance X. You have to manipulate it in certain ways. The details we don't need to worry about because we have to make the things kosher with the laws of probability. But what chi-squared will do is will determine the probability of finding the electron at this distance out X when you measure it. The measurement has to come first. Tell me an X. Tell me where you're interested in finding the electron, how far away from the nucleus, and now tell you the probability upon taking a random measurement of finding it there. Yeah, it's a complicated interpretation. It's a long way from the simple trajectories of Newtonian mechanics. It's a long way from the Bohr orbits of those nice circles of their different distances, circles getting bigger and bigger and jumping from one radius down to another. All of that is gone. All that we can have are probabilities. Let me give you one analogy and then I'll stop for a question. Let us take the classical case of a pendulum. Right? A pendulum swings back and forth. And as the pendulum swings back and forth, its X and Y values are changing, right? Here's the X value of the pendulum, and here's the height of the pendulum, the Y value. Let's simplify things, and let's just worry about the X value of the pendulum. Imagine I had a little light, attached to the pendulum, shining down on the ground. And as the pendulum swung back and forth, I watched the light swing back and forth along the ground. I'm only interested in just the X coordinate, trying to isolate it to just one dimension, okay? As the pendulum swings back and forth, the light swings back and forth from -1 to 1. Okay? That's what the light will do. Can I predict, the position of that light at any time? It'll go from 0, it'll go out to 1, it'll go back to 0, it'll swing down to -1, go back to 0. The light will swing back and forth and back and forth as the pendulum above it swings back and forth. Yeah. I can write down a Newtonian equation. This is not an energy equation. This is actually a force equation. Detail, not important. Point is, there is an equation which will describe the forces involved on this pendulum. One of the parameters here, L, is simply the length of the pendulum. Okay? G is the force of gravity. Clearly, gravity is what's making the pendulum move back and forth. This is a differential equation. A Newtonian force differential equation. This tells me how X is changing in time, and this tells me, well, here is the function itself. How it changes in time actually depends upon the value of the function itself. The details are not important. Point is, it has a solution. There's an answer to this differential equation. There's a dependency of X upon time, which makes this equation true. And not surprisingly, this is, in fact, the solution to this physical situation. It is, in fact, a sine curve, okay? Right, the pendulum, the light shining down will go from 0 up to 1, then back to 0, then down to -1, then back to 0, and that's exactly what the sine curve is doing. It goes from 0 up to 1, back to 0, down to -1, back to 0, up to 1. This, in fact, is the solution to this equation. This is why I picked the sine curve. Not only is it the simplest, but I wanted to give you a physical example where the sine curve is, in fact, the solution. But this is a Newtonian solution. Okay? This is a classical solution. This tells me exactly where the light is shining at any time. You give me a time, and I'll tell you where the light is shining. It's shining someplace between 1 and -1, and it changes according to this curve. Imagine if I could not do this. Imagine if all I knew was the probability of where the light is shining, given me any X. Here the graph would look like this. Notice that the probability is 0 anytime beyond -1, and I'm sorry, any place beyond -1 and any place beyond 1. The pendulum never gets here. And so the probability of finding the pendulum there is 0. And here would be the probability curve of the swinging pendulum. Notice that the probability is lowest at the 0 point. It's not exactly 0. This should be a little bit higher, okay? But it is certainly the lowest probability. Why? Because the pendulum is moving the fastest at the bottom. It's spending the less time there than any other place. This is where the pendulum is moving the fastest, and it sweeps right through it. But as the pendulum rises, it goes slower and slower and slower until finally it stops, turns around and starts coming back the other way. Here is where the pendulum is moving slower and slower, and it's spending more time here because it's moving slower. And so the probability of finding the pendulum, taking an arbitrary time, imagine I put this pendulum in a black box, and I just had a strobe light that would turn on at random times, and all of a sudden I would see the pendulum, and I would notice where it is underneath the X value. And I would say, given the fact that the strobe light would turn on some time, what's the probability of finding the light at -3, at let's say, well, at point -3, at 0.7, some number between -1 and 1. That's what this curve would tell me. It's not this curve. Okay, this is more like a parabola type curve. Suppose that instead of having an equation that could give me a definite trajectory solution, this tells me exactly where the light is shining, what place on X is illuminated at any time. All I could know would be the probability of saying that the light is shining at this place X at any arbitrary time. That's the limitation of quantum mechanics. That's the limitation of the Schrodinger equation. Okay. That's my attempt to try to explain what the Schrodinger equation is saying and what the solution to the Schrodinger equation is saying. Let me just summarize before I take any questions, if I've not have you all glazed over by now. The Schrodinger equation is an equation about the conservation of energy. Its solution is a wave. It's a very complicated wave. The wave actually can even change in time. The wave is a three-dimensional wave. The full solution, you have to give me a full point in space, and I'll tell you the height of the wave. We can cook up a simple example of an atom, a simple electron in its ground state, and all I need to tell you is how far away the electron is from the nucleus. I just need to give you one number called the X number. I can give you a Schrodinger equation that just involves the wave equation for just the value of X. Okay, how far away is the electron from the nucleus, and I'll give you a wave equation. I'll give you the wave function. But what is it telling me? It's not telling me anything actual physical direct. There are many things I can extract from the wave function. I can extract the energy of the electron. I can extract the probability of its position. You give me a position, and I'll give you the probability of finding the electron in that position. You give me a momentum, and I'll find you the wave function. I can calculate from it with other manipulations the probability of finding the electron having that momentum. All that I can do is calculate probabilities from the wave function. And the physical manifestation of those probabilities, really quite fantastically, is the square of the wave function. So the wave function does have some kind of relationship, clearly, with the physical world. Okay, its square tells me probabilities. But just as this equation here tells me exactly where the light is shining, I will never get this from the solution to the Schrodinger equation. I will never be able to tell you exactly you give me a time and I'll tell you what place the light is shining. Schrodinger equation can't give me that solution. It can only give me, and I'm trying to give the analogy, It can give me the probability of you give me a place, and I'll tell you the probability at an arbitrary time of that particular point being lit up by the light shining from the swinging pendulum. Okay, let me stop here and take a breath and see if anybody if anybody has the ability even to ask a question. Greg, do we have any questions?
Hi, Peter. We do not have any questions.
This does not surprise me. Okay, this is the reason. By the way, guys, this is the reason. Now, I am not, of course, the best person to do this. I'm sure there's someone who could do this much better. But this is why when a speaker is giving an hour lecture on quantum mechanics and they talk about the wave equation, all they do is they take their hand in the air and they wave their hand. Because to try to give some kind of an explanation for it without really going into the math is very difficult. I hope I've given you some idea that the Schrodinger equation has a solution called the wave function, and the wave function is not this mysterious thing. It is a function which simply is a computation device that tells me, you give me, in most general case, a point in space, and I'll give you a number associated with that point in space. It's more complicated. In fact, it's not a number, it's a complex number. Yeah, it's very complicated, much more complicated than I've given. And the function not only depends upon the place in space, but also the time in which you've asked me, because this function is changing. It's convoluting all the time. Okay?
Peter, we just got a couple of questions if you want to take them.
Okay, great.
From Bill Gunther, what is K in the last equation?
K is called the phase angle. It just simply tells me where the sine curve starts at the origin. It doesn't really have to start at 0. It could start up at the top at the amplitude and work its way down. Okay, K just tells me where the wave starts when I'm looking at the origin.
And one question from Sharon Beatty. Total probability under the curve still has to be 1, correct?
Yes, very good. Thank you for pointing that out. That's why the psi squared itself doesn't immediately give me the probability. Okay, psi squared has got to be massaged so that rules like that, what Ann just said, have to be true. This is a pretty mechanical, mathematical thing to do. The physicality, if there's any at all, of the wave function is in its square, but it won't literally give you the probability. It's massaged so it mathematically will conform to the laws of probability. For example, the area under the full probability curve must always be 1. It simply says in words, well, something's got to happen. It's got to be somewhere, okay? Rules like that. All right. So when we go to the solution to the wave function can be pictured in a way like this. Here's the hydrogen atom. Here's at the first energy level. Here would be at the second energy level. Those are those the original quantum numbers of Bohr. 1, 2, 3, 4. 1 was the first radius, and 2 was going to indicate the second radius, and 3 was going to the third radius out. Okay, those are all gone. Okay, because as Born said, it is necessary to drop completely the physical pictures of Schrodinger. Never mind the pictures of Bohr. Okay, Heisenberg told us to drop the physical pictures of Bohr. Born is saying we have to drop this attempt of Schrodinger of trying to say that what this wave function is showing us is the amount of the electric charge. Electric charge electron is, you know, one electric charge, some number of times 10 to the minus 19th coulombs, a tiny, tiny amount of electric charge. That wave is not showing us how the electric charge is smeared out in space. No, it is necessary to drop completely any physical picture that Schrodinger aimed to bring back this classical picture. Going back to Du Bois' picture. No, we have to drop any idea that what this wave is doing, okay, is showing us exactly what the wavelength is that'll fit exactly around a Bohr radius. No, as pretty and as nice as those ideas were, no, they're hopelessly wrong. Okay, they work for one simple case, the ground state of the hydrogen atom. It works for one atom, the hydrogen atom, for only one of its energy states. Only one, the lowest. Even when you go to the second energy state won't even fit exactly the right number of de Broglie. No, all of that will not work. All that we have is this incredible equation that Schrodinger comes up with, but it needs to be interpreted properly. And all that we can retain is the formalism. That's just a simple way of saying the mathematics, the mathematical formulas and uh, uh, devices that are being used, the methods that are being used. But we must fill it with a new physical content. And that physical content, as I say, the square of the wave function will give us the ability to compute the probability of finding the electron at that place if you should choose to look for it there. So if, for example, if you had the ability to just watch one place in the atom, one distance from the nucleus, and just watch it, okay, how many times would the electron appear at that place, within an hour? Okay, I'm using simple, silly examples just to try to make the point. I just keep watching that one place. How often will the electron appear at that one place? Well, it'll depend upon the probability of it being there. For example, if the probability was a half, let's say, the probability of that place had a value computed from the wave function squared of a half, I would expect at half the time the electron would be there. And the other half of the time it would be someplace else. What half of the time? I have no idea. You give me an arbitrary strobe light place and is the electron there? I have no idea. All I can tell you is I've got a 50-50 chance of it being there at that arbitrary point. If I keep watching it continuously for an hour and I add up all the little times that it was there, I'll get a half hour. This is as much as we're ever going to know about the position of any of the electrons in the atom. Okay? That's what we have. Einstein was not happy with this interpretation. He saw the benefit of it. He saw that you could begin to build technologies on top of this interpretation. Absolutely. All the technologies of quantum mechanics, okay? Everything that we've talked about, the lasers and things that we haven't talked about, solid state physics, semiconductors, is all based upon these probabilities. Because we're always dealing with gazillions of atoms, gazillions of electrons. And the probabilities are good enough to build technologies on top of it, just as the laws of thermodynamics only talk about probabilities. Okay? We never know the position and the momentum of any one gas atom in a box, but I can give you precise laws about how the pressure and the temperature are related inside that box, even though I know it's being created by gazillions of atoms smashing into each other in the sides of the box. I will never be able to figure out all those details, but I can give you very precise laws about how the pressure and the temperature will change as I change, for example, the volume of the box. I have exact laws of thermodynamics which will tell me those things, and I can build all kinds of technologies like steam engines using those laws. Okay? We can build very sophisticated technologies based upon these probabilities, but they don't tell us exactly what's going on. They only tell us, well, what they claim to claims to tell us what it's saying. And the famous quote that you hear all the time comes from this reflection of Einstein on the Born interpretation of the probabilities. The theory, quantum mechanics, says a lot, but does not really bring us closer to the secret of the old one. I, at any rate, am convinced that he is not playing dice, okay? That there's something more to this. There's some deeper theory that this quantum theory ultimately will be replaced by, which will come back and tell us exactly what is going on. What the trajectories, if the electrons truly are moving, it'll give us the trajectory of the electron as it moves within the atom, just the way I could give you the exact trajectory of the swinging pendulum. I understand that this equation, the Schrodinger equation, does not give me that. I understand that. I understand exactly what it does give me. And I understand that it tells me a lot. But it is not ultimately what a physics theory should do. A complete physics theory should tell me more. And Einstein died in 1955, still believing that there was more to the theory than what the Schrodinger equation and the dirac equation and all the rest of the discoveries of quantum mechanics could provide. But to go and see what it can provide, here are some examples of real squares of wave functions. These aren't wave functions, these are squares of wave functions. That's why they're all above the x-axis. They all have positive values. And here are the three simplest energy levels of the three first energy states of the Bohr atom. Okay, this is energy level 1, energy level 2, and energy level 3. Okay, this is so that when you drop from 3 down to 1, and 2 down to 1 and 3, this is where you'll be getting all the different spectra. You'll be getting all the light colors coming out as you move from one energy level down to a lower energy level. These are the squares of the wave functions. Okay? And here is the simplest one of all. Okay, it's the lowest of these wave energies are called S's. We'll see that in a minute. But at the first energy level, here is the square of the wave function. Notice it has one high peak. Here is the square of the wave function of the second energy level. Okay? When you excite the hydrogen atom to a higher level, the second level. Here, the most probable place where you'll find the electron from the nucleus, here's the nucleus here, is out this distance here. Notice it has a small peak. This is not the second most highest. No. You'll have a much higher probability of finding the electron here at this further distance out than here, because this is higher, just simply a higher value. But there is this peak here, and then it drops down to 0. Okay, you do not expect to find the electron if it's in the second energy shell. Do not expect to find the electron here. You've got a 0 probability of finding the electron here, and the electron's probability of being further out from the nucleus rises higher and higher until it reaches its peak probability and then finally drops down to 0. When you get out to these distances here, you're virtually at a 0 probability. Do not expect the electron to be this far away from the nucleus in the second energy level. And this is where, with the electron is in the second energy level, this is the end of the atom. Okay? This is the furthest radius of the atom. There's no more chance of expecting to have any part of the atom this far out from the nucleus. And here would be the square of the wave function of the third energy level, the simplest example of the third energy level. It has similar peaks with the highest probability being out even at a further distance. So here are examples of not the wave function itself, but and not even the square of the wave function, but the square of the wave function massaged so that it fits the laws of probability. And you comply with experiment. Okay. One of the great triumphs of the Schrodinger equation was when it took that lowest energy level of hydrogen and found the wave function and took its square and took the highest probability. What was the place that had the highest probability of finding the electron there? Son of a gun, if it wasn't exactly the Bohr radius, if it wasn't that A0 number that Bohr had predicted 10 years before as that lowest orbit size for the ground state. That's gone, but yet that number survives as the place where you'll be most likely to find the hydrogen electron when it's in the lowest state. Okay. Okay, so here are the 4 quantum numbers. This is Bohr's original number. These are the shells. Have quantum numbers 1, 2, 3, 4. Here are originally the Sommerfeld quantum numbers, the second quantum number and the third number. These must be totally interpreted now in terms of, in context of the solutions to the Schrodinger equation, to the various different possible wave functions. And here's the last quantum number, the spin. That's an easy one. Spins, it can just be -1/2 and +1/2. So the shells are easy. The shells are just the integers, 1, 2, 3. But the subshells, which are listed by L, and even the so-called orbitals inside the subshells listed by M, are more complicated, but they're not really too bad. Okay? Let us go through these, not with this chart here, but let me show you more visually. Before I do that, let's just take one more peek at the actual wave functions, or the squares of the wave functions. Let's take a look at the hydrogen atom, and let's look at the second energy level, okay, the second shell. Okay? And I want to look at that first subshell where the L number is 0. And that's called 2s. The shells are called S, P, D, and F. Those are the letters. They're important to remember. S, P, D, and F. So here's the second energy. Here's the first subshell of the second energy level. So here's that 2s we were just looking at. Yeah, we just were looking at this thing here. If we stay at the second energy level and go to the second subshell, L being 1, here now we're looking at the P energy level. And notice it doesn't have 2 bumps. It only has 1 bump. So the wave equation, the wave function of the second energy level, the solution, when you put in the second energy level of the potential energy, the solutions that you get don't have 2 bumps. It only has 1 bump. These are the values that we get out of the Schrodinger equation. More so looking at the third energy level. Okay? Here again, we're looking at the simplest, lowest subshell of the energy level. There's that third one that we saw just a moment ago. And here now we'll jump all the way out to L is equal to 2, where there are, in fact, 5 different orbitals in that subshell. Here they are. Here's a distribution here. And again, we get more or less of a smooth probability distribution for all of the energy level, all the orbitals in that third energy level. I'm sorry, in the third shell of the third energy level. Yeah, I know, it's confusing. Let's see if I can clear up the confusion a little bit. Here are the subshells, right? We have the shells. The shells are simply numbered 1, 2, 3, 4, 5. Those are Bohr's original orbit sizes. Every shell has a varying number of subshells, but they're not so hard. The first shell has 1 subshell. The second shell has 2 subshells. The third shell has 3 subshells. Okay? Not all that difficult. Okay? Those numbers are detected by the L's. Okay? So this is the second quantum number. For some crazy reason, which we'll see in a minute why it's not so crazy, the L's numbers start not with 1, 2, 3, but they start with 0. So here's the first subshell. Everybody has a first subshell, no matter what energy level you're at, no matter what shell you're at. The second, the third, the fourth, all these shells certainly have a first subshell, because the fourth shell has 4 subshells, and it certainly has a first. Here's the second subshell. It has 3 orbitals. The third subshell, if you have enough energy to have a third subshell, has 5 orbitals. And finally, if you have a fourth subshell, it'll have in it 7 orbitals. This looks like numerology, right? We have these 1s and 2s and 3s, and then we're going up with odd numbers, 1, 3, 5, 7. This numerology, guys, it does look like numerology, but it's coming from the solutions to the Schrodinger equation. Okay? You're looking at the quantumness of the energy values and the orientations of the shapes of the squares of the wave equations. For example, the first shell is perfectly symmetric. That was the one I was trying to show you. Doesn't matter what direction you go from the nucleus. You can go to the left, you can go up and down. It's going to look the same. It's going to have a certain waveness to it. It's going to have a certain peak at a certain place. It'll be lower, it'll rise up, it'll go back down again, it'll go up and down a couple of times, but it'll basically be a symmetric type shape. Doesn't matter what direction you move from the nucleus, it'll have a spherical kind of shape. When you go to the next subshell, now we have 3 orbitals, and they're orientated differently in space. They look like dumbbells. One can be oriented along the x-axis, one can be oriented along the y-axis, and one along the z-axis. What are these shapes? These shapes represent the square of the wave function. It shows you the outer kind of envelope, the skin of where you'll find the electron 90% of the time within these shapes. You'd have to go in and actually look at the real wave function squared to see how those shapes vary, how those probabilities vary inside these overall shapes. But generally what you're shown in the textbook is just the overall skin of the shapes. Here's the 5 suborbitals in the G subshell. Notice they're orientated in different ways. Some even have different fundamental shapes. The first 4 are like clovers, and the last one has this weird kind of shape. The 7 suborbitals are even weirder. Okay. Again, these are just the skins where 90% of the electrons can be found. Okay. So the subshells are listed by the L number, and maybe this might make a bit more sense. The first shell only has a 0. The second level has a 0 and a 1 for L, two subshells. The third can have 3 subshells, 0, 1, and 2. The fourth shell can have 4 subshells. Okay. And each one of these subshells have a definite number of orbitals, okay? Number of subshells within it. Even the scientists knew not to call them subshells, so they gave them a different name, very unfortunate name, orbitals. These are not orbits. I don't know why they called them orbitals. I guess maybe to remind us that they once were thought of, or they could have been orbits, but they're not. But they use the word orbitals. And so the subshell, the S subshell, there's only one of them. Everybody's got one. Everyone has a 0 S subshell. And because you can spin up or down, there are 2 electrons in each orbital. So that's why when you get 3 p orbitals, you'll get 6 electrons. If you have 3 orbitals, you'll get, 5 orbitals, you'll get 10, and finally 7 orbitals, you'll get 14. So remember these numbers, 2, 6, 10, and 14. This is the size of the number of electrons in the various orbitals. I see I'm running out of time. Maybe I was too ambitious in trying to explain this. I did not realize it would take this much time to get this far, to try to get to what my goal was for the whole course, was to explain the periodic table. Let me jump in the last 5 minutes to the periodic table. Before I do that, here are the energy levels of the orbitals. They start off very simple. The first energy level is at the lowest. The number 1 is at the lowest. And then the two subshells of number 2 are the next lowest. But then it gets a little weird. The third energy level, yeah, the first orbital is good, the second orbital is good, but the fourth energy level sticks in there. Before we get the complete story of energy level 3, the fourth energy level, that lowest orbital, is actually of a lower energy level than the third guy. And it gets even more complicated. Before we can finish the fourth energy level, the fifth energy level sticks its nose in there, the sixth energy level. So this looks, in fact, quite complicated. It's not as complicated, though, as it looks. There are patterns here. Okay, let me just show you the simple pattern. Then I'll show you I want to hold out 5 minutes to show you the periodic table. If we take those orbital and write them out in the simplest way possible, here's 1s, here's 2s and 2p, right? Here's the first subshell and the second subshell. For the third energy level, first subshell, second subshell, the third subshell. Remember, for every energy level, the 10th energy level has 10 subshells, right? Here's the fourth subshell, fourth energy level. I'm sorry, it has 4 subshells. Couldn't write them out in any simpler way. I'm just really following the L numbers. Now let me do a cute device. Let me look at the rows this way with these diagonal arrows. Son of a gun if this doesn't produce this chart. Here's 1s, yes. Here's 2s, true. Here is 2p and then 3s. Yes, 2p and then 3s. Here is 3p and 4s. Yeah, 3p and 4s. Here's the first long one. You get 3d, 4p, and 5s. Yes, 3d. Yeah. Going down, following these arrows, writing them out in the simplest way possible, but taking the rows in these funny arrow directions, I get exactly the order of the energy levels, okay? Which is how the electrons will fill themselves into the atom. Is this just some kind of a funny trick? These arrows? No. If I simply number these rows 1, 2, 3, 4, 5, 6, 7, etc., what these numbers represent is nothing less than the sum of the first 2 quantum numbers, n and l. This is 1 plus 0. This is 2 plus 0. This is 2 plus 1 and 3 plus 0. This is 3 plus 1 and 4 plus. I'm simply adding up the n number and the l number in each of these rows are the same. And that's what determines the energy levels. Okay, with that, I think I can only get as far as this. Here is what I've been trying to get at. Here is the periodic table. What are these colors? This is the first subshell. This is the so-called s orbitals. This here is the second subshell. All these elements have in them electrons which are filled up in the second subshell. Here are the elements that have their electrons filling into the third subshell. Of course, you've got to be out to the third energy level to even have a third subshell. That's true. And finally, here are the elements that have a fourth subshell. And they fill up, these are the sizes of the radius, which we won't have time to do. But here's the first energy level. These numbers here are just simply the energy levels. Here's the second. Okay. This is the s orbitals, and here are the p orbitals. Remember, there are always 2 in s. S always has 2. S has just one subshell, but there are 2 electrons in each subshell. Right? So all of these always have 2. These always have 6, right? Because there are 3 subshells, and everybody gets 2. Here is the next set of 3. 2, 6, and 10, because there are 5 subshells, and everybody gets 2. Okay? And so on. This was the dream of Mendeleev. This was the dream of Bohr. This was the dream of all chemists, to understand what is the structure of the periodic table. And I'll leave you with this one. This is a live link. You'll come out on your presentation as well. Choose this one here. Choose the electron version of the periodic table. You'll get those colored blocks just as we saw, the same colored blocks for the same reason, the S block, the P block, the D block, etc. But if you just hold your cursor over the different elements, you will see 2 things. You'll see the picture as I can't, once I move it out of the way. You'll see the electrons beginning to fill in. You see the electrons filling in? As you just fill it, move it over. And I'll leave you with one last idea. Look at the simple noble gases. Look at the electron configuration of the noble gas of neon. All of the blocks are totally filled in. That's why they have no need to interact with any other element. And as I go down this list, as more and more blocks get filled in, if a block is filled in, it is filled in completely. This is what makes the noble gases the noble gases. And I can explain all of the chemical, well, I can't, chemists are still in the process of explaining all the chemical properties by how the electrons fill into their energy level. One more one just for fun. What are the three best conductors of electricity? Copper, silver, and gold. Copper, silver, and gold. Look at the energy configurations. Look at copper. It has one guy sticking out there in the S. Silver has one guy sticking out there in the S. And gold, he's got one electron sticking out there in the S. This is what makes these three elements. They are metals, so they have a crystal structure to them, and they have one free electron which can carry the electron current. We could do this all day, okay? Looking at various chemical properties, and they're being reflected in how the electrons, particularly the outer electrons, are filled in to the energy levels. All of this is dictated by the combination of the Schrodinger and dirac equation. Okay, and that's as far as we can go, guys. I apologize for being too ambitious and not. Let me stop this here. Okay, so I want to thank you for your attention for this very difficult class. I hope I gave you some indication of where this is. Some of the talks that I suggested in my emails will go further in my information, not maybe in the details of the energy shells, but it'll give you maybe a broader idea where this energy shell stuff can make more sense to you. All right, I don't think there's really any time for questions, but if there are any, I just want to thank everybody for their attention. I hope we got a chance to take a look at my little write-up for what I'm proposing for next year. We wouldn't be going something as difficult as the Schrodinger equation. That math we would stay away from next year, but I would try to give you an idea of what the calculus is about. I've been asked a number of times by various people, could you give a course maybe and tell us what is the calculus about? This is my attempt to maybe give a course that might be of interest to some of you. Okay. Greg, are there any questions outstanding?
There are indeed. Let's see, from Andy Chapman. Does this equation and the associated probability have an application in research with particle accelerators like the research done at Fermilab?
Oh gosh, the whole other presentation, which I foolishly mailed to you, which we didn't even get a chance to even look at, is all about the first initial developments of the nucleus. And in that presentation, we see the discovery of the quantum nature of the nucleus, and antimatter is there, and all kinds of other wonderful things, which all lead to the the current research today on particle physics with the high energy colliders. It all begins in the 1930s by looking at the quantum nature of the nucleus itself. We never even got a chance to even broach that idea.
And Jim Talbert asks, has the discovery of subatomic particles, quarks, etc., resolved the particle wave dispute at all?
No, the controversy still rages as to just what exactly the equation is trying to tell us. Everyone, though, can agree upon one thing, and this is quite amazing. The Schrodinger equation itself, its solution, the wave function, has no physical meaning. This is quite amazing. All physicists can agree the actual function itself, that wave, not its square, but that actual wave itself has no direct physical meaning. as for example, the sine curve that I showed you for the pendulum, that is exactly the place where the pendulum is on the x-axis. It tells you exactly what the wave function does not tell you anything directly physical about the world. This is an amazing statement about quantum theory. And because everyone can agree upon that, we can't get an agreement upon about what the equation is saying about reality. And there are the different interpretations. And there I send you to the people like Sean Carroll, who will try to give you a better idea than I can of what those different interpretations are.
And Joe Parisi asks, has the Schrodinger equation ever been verified by experimentation? Can it ever be verified?
No, it's verified every single day. That's where all the technologies, all the quantum technologies are based upon the probabilities of the Schrodinger equation. I tried to give the analogy to the laws of thermodynamics. The laws of thermodynamics are all statistical laws, but yet we can precisely know the pressure and, for example, the temperature of these gases, even though they come from the individual zillions and zillions of subatomic particles. We can still talk about the laws of pressure and temperature. We can build detailed technologies like electron microscopes and semiconductors from the statistical probability laws that the quantum mechanics obeys. They are all that we need to build technologies, just as the laws of thermodynamics are all that we need to build steam engines. They are verified every single day.
Edward Latowski, we have discussed the wave equation for an electron bound to an atom. How does one obtain the wave equation for an electron in free space that is unbound to an atom? As a limiting case.
It's the same Schrodinger equation. It'll have a different potential energy function. Its rate of change in space will be different. So the equation will have a more complex terms to it, and its solution is harder to find. You have to use approximation methods using supercomputers to find approximate solutions of what the wave function looks like. But you know, that's what they're able to do. They're able to take these more complex scenarios than a simple ground state electron atom and find solutions to those more complex equations. And of course, not surprising, they're more complex wave functions, which will have more complex probabilities.
And I just have a quick question. Since Einstein's death, has there been any research or math or data or anything that suggests his belief upon his death?
Absolutely. There are some people who are right with Einstein that they don't want to accept that the Schrodinger equation is the end of the story. They just feel that no, we should be able to get to know something beyond the probabilities. That's a minority. Most physicists, most scientists believe that the best we're ever going to get in the quantum world are probabilities, but there are some people, the so-called hidden variables crowd. That's one interpretation that you can hear about in the lectures. That crowd still is looking for some more variables which we don't yet know about that'll give us direct trajectories. Most people don't believe it.
And that's all the questions, Peter.
Okay, guys, thank you so much. Have a great summer, and hopefully we'll see you in the fall.
Thank you. Thank you so much.
Please, thank you. Please send me an email if you have any thoughts about the math course. Any thoughts at all, good, bad, whatever. If you've got a thought, I appreciate it.
Thank you.
All right, guys, I'm going to stop the
Okay.
and say goodbye. All right.
Goodbye.